let me ask you something. Have you ever actually stopped to think about what happens when we start treating AI agents as, full-fledged team members, but we're only managing them with polite little text prompts? I mean, what happens when your AI developer, which has repository access and deployment capabilities, by the way, basically goes rogue just because it lost the plot in a long context window? So the crucial point here is staggering. According to a 2022 study by Pierce and his team, roughly 40% of Copilot-generated programs they looked at were found to be vulnerable. 40%! And we aren't just talking about a missing semicolon or a simple syntax error. We're talking about hard, exploitable security weaknesses. The stakes for getting AI integration wrong in software development are already massive. And honestly, as we scale up from simple autocomplete tools to fully autonomous agents, those stakes, they are only getting higher.
Welcome to today's Explainer. Today we're unpacking some really fascinating AI news based on a recent arXiv paper titled Specifying AI-SDLC Processes, a Protocol Language for Human Agent Boundaries. The researchers are bringing a proposed solution to this whole rogue AI problem. They're introducing a brand new domain-specific language, a DSL, that is specifically designed to structurally enforce AI workflows. Basically, it's about transforming AI coding from a wild, unpredictable experiment into actual, auditable, deterministic engineering.
To solve this chaotic multi-agent problem, here is our roadmap for today. We'll hit the AI specification gap, policy versus structural enforcement, capability boundaries and tokens, the 2+N team pattern, bounding system failure rates, and finally, process as the new asset. Okay, let's dive right into this with Section 1, the AI specification gap, and moving beyond ad hoc tools. To really grasp the problem, we've got to redefine our landscape using this term, AI-SDLC. That stands for AI Integrated Software Development Lifecycle. We're talking about a process built around true collaboration, where AI agents are actual first-class team members. They plan, they write code, they validate, and they review. We're not just taking our old human-centric processes and speeding them up with a shiny new tool. No, we need entirely new processes, optimized for real human-agent teamwork. The big challenge is figuring out how to clearly specify who does what, when a human needs to step in, and what rules literally cannot be broken. Because honestly, when we don't specify those rules, things fall apart fast. Just look at these documented AI coding failures. We already touched on the security vulnerabilities, right? But then you also have these silent failures, where the code doesn't outright crash, so it looks fine, but it completely fails to do what it's supposed to do. Then there's context overload. You've probably seen this. The agent just spins in circles, repeatedly applying the exact same broken fix. Plus, if you're in a regulated industry, this autonomous generation creates an absolute nightmare for audit trails. And maybe the most dangerous one? Having a single agent review its own output. It's basically grading its own homework against the exact same flawed model it just used to write it. The sources make a really vital point here. These are process problems, not capability problems. Throwing a better, smarter AI model at this won't fix a workflow that is fundamentally broken. Which brings us to Section 2, policy versus structural enforcement, because the mechanism you use really matters. And this brilliantly illustrates the core thesis of the paper, contrasting two completely different approaches. Right now, most of us rely on behavioral compliance. We just type our standard operating procedures into the agent's prompts and cross our fingers. But that is incredibly subject to drift. It relies 100% on the agent's interpreting and actually remembering those instructions, even when it's under pressure from a maxed-out context window. So the researchers propose shifting to structural enforcement instead. By using a domain-specific language, we can build actual infrastructure-level gates. It explicitly separates the policy, which is what we want to happen, from the hard mechanism that physically forces it to happen. Let's move to Section 3, Capability Boundaries and Tokens, to see how this DSL actually works under the hood.
The language relies on 4 absolutely critical invariants to keep things locked down. First up, token integrity. Validators issue these cryptographic or logical tokens, and the agent literally cannot forge those signatures to skip a step. Second, capability boundaries. Agents only get access to specific tools based on their current operational mode. Third, non-overridable blockers. If a security validator spots a critical issue, boom, it's a hard stop. The agent cannot talk its way out of it or override it. And finally, number 4, audit completeness. This guarantees a permanent, immutable log of every single action taken.
So here is how that deterministic loop actually plays out in practice. A validator agent, or even a whole group of them, evaluates a task. If they reach a unanimous or majority pass, they issue that unforgeable validation token. And only when it has that specific token in hand can the orchestrator dispatch the next step in the execution. But if there's a split decision or a hard blocker is found, the infrastructure literally stops the agent in its tracks and forces a human to step in. It's such a brilliant system because it treats AI workflows like a strict state machine, governed by unbreakable formal rules. Okay, Section 4, the 2 plus N team pattern. This is their reference configuration. To make this work, the framework proposes what they call the 2 plus N team pattern. The number 2 here represents the absolute bare minimum number of human and control roles you need, specifically an architect and a reviewer. This hardwires the classical IT security principle of separation of duties right into the workflow. A single human shouldn't be able to independently validate their own work, and that rule absolutely still applies, even when they're using AI assistants. And the N? Well, that represents your specialized AI agents. They're out there doing the heavy lifting, writing the code, running the tests, generating documentation, all of that. But because of those capability boundaries we just talked about, the infrastructure strictly prevents any role contamination. The system ensures that an agent working in producer mode absolutely cannot touch the tools reserved for reviewer mode. So a coder agent literally cannot merge its own pull request. I don't care how clever your prompt is, it just can't do it. Now, what's really interesting about this next part is Section 5, bounding system failure rates. Here is the mathematical proof. There is just a stark contrast in how failures propagate between these two methods. When you're relying on those behavioral prompt-based workflows, errors cascade. It's like a domino effect. If an agent skips a validation step or hallucinates early on, every agent downstream is suddenly operating on corrupted data. The failure rate snowballs. It leads to this cumulative, saturating failure growth across your whole pipeline. But with structural enforcement, that cascade hits a brick wall. The blocker is physically halted. Mathematically, the system failure rate is strictly bounded to a weighted product of the individual agent's failure rate and the validator's failure rate. This is a massive paradigm shift for us. Now, it's really important to understand that structural enforcement doesn't magically make AI models themselves deterministic. Large language models are always going to have some inherent randomness to them. But what this protocol does is eliminate process non-determinism. An agent can no longer accidentally skip your testing phase just because it got a little confused. By locking down the structure of the workflow itself, the residual non-determinism of the AI is kept in a very tight box. It makes the entire system quasi-deterministic, incredibly safe, and, crucially, fully auditable. Let's move right into Section 6 and see how this builds into our final point, process as the new asset, and really, the future of AI-SDLC. The source material wraps up with this really profound observation. Quote, "The protocol is institutional memory, models are commodity infrastructure." Just think about that for a second. As foundation models like GPT, Claude, Gemini, as they all converge in terms of capability and quality, your specific choice of model is going to matter less and less. Soon, everybody is going to have access to the exact same brilliant AI coders. So what sets you apart? Your team's custom protocol design, how you structure those boundaries, your validation gates, your 2 plus N human integrations, that is going to be your only true, durable, competitive advantage. It's honestly just like the evolution of cloud computing. We used to differentiate based on our physical servers, right? But now, we differentiate on how we architect our cloud services. Models will commoditize, protocols will differentiate. The days of just tossing a few prompts at an LLM and hoping it writes secure code, those days are ending. Structural enforcement is absolutely the future of the AI-integrated software development lifecycle. So, as you look at your own engineering pipelines today, I want to leave you with this. Are you just trusting your AI to politely follow the rules, or are you structurally enforcing them? At the end of the day, who or what is really managing your AI?